and University of Virginia, we will host the Open BME Seminar Series this spring 2021 to bring together faculty and trainees from around the globe to share in the excitement of and conversation about cutting-edge research in bioengineering. All Open BME seminars will take place at 3 p.m. Central, 4 p.m. Eastern on Thursdays, with more information to be found on each speaker at openbme.org. We have many names to thank in bringing this series together, and today I'll start by thanking Professor Chow Zhou and Karen Teasdale of Washington University for today's seminar, and Case Western for providing streaming services to YouTube. And now it is my honor to introduce the first speaker in the Open BME series, Dr. Bruce Tromberg, Director of the National Institute of Biomedical Engineering and Bioengineering at the National Institutes of Health. Dr. Tromberg is going to share a story of the RADX Biotechnology Initiative launched just a month or so after COVID reached our shores to support diagnostic testing at point-of-care facilities. This remarkable effort mobilized research and industry labs across the US and led to a lasting technology transformation that we'll learn about today. Prior to joining NIH in 2019, Dr. Tromberg was a professor of BME and surgery at University of California, Irvine, where he directed the Beckman Laser Institute and Medicine Clinic and an NIH National Biomedical Technology Center. He built a highly productive research program in optics and photonics for biomedical imaging and therapy. He began with a bachelor's degree in chemistry from Vanderbilt University and was an Oak Ridge Associated University's fellow while he earned his master's and PhD in chemistry from University of Tennessee. Now a fellow of the Optical Society, AIMB, Society of Optical Engineering, Dr. Tromberg has published more than 450 publications and 21 patents. He's a founder of the biophotonics company Modulum. He's received several honors and awards, including the Michael Feld Biophotonics Award from the Optical Society of America, and has trained more than 80 students and fellows. Thank you so much for joining us today, Dr. Tromberg. And as I turn the screen over to you, I want to remind participants in the audience to enter questions into the Q&A, and Dr. Tromberg will address them at the end. Thank you so much.
Thank you. Thank you very much, Lori. And thank you for that very kind introduction. It's so exciting to be here. This is such a wonderful idea for a seminar series. And I'm just so honored and pleased to be able to be the first one to kick it off and tell you about the story of RADX and also fill everyone in a bit on the background of NIBI, tell a little bit of our history. So I'd like to start out with that. And here is a picture of about half of the institute. We're not a big institute, fairly small of the 27 institutes and centers at the NIH. But as Lori pointed out, we've been given a disproportionately large task for the size of the institute, but certainly not for the scope, impact, and ambition of our entire community. So I think we can all be inspired by what we have done collectively as a community. So thanks to all of my colleagues at NIBI, some of whom are pictured here, and I'm looking forward to our ability to return to the workplace and take another series of updated photos as we've continued to expand. As I mentioned, I'd like to tell a little bit of a story about NIBI. Where did we come from and how did we get into this position? It's interesting to go back to the end of 2000, December 29th, 2000, when Bill Clinton was president. Here's a picture of Rod Pettigrew, the founding director of NIBI with Bill Clinton. And NIBI was created by a law, public law, an act of Congress. And if you look at the language of the act, it is really quite inspiring and forward-thinking, since this language was probably written in the mid to late 1990s. So here's what it says. I'd like to kind of read it for everyone. The Congress makes the following findings. Basic research in imaging, bioengineering, computer science, informatics, and related fields is critical to improving healthcare but is fundamentally different from the research in molecular biology on which the current national research institutes at the NIH are based. To ensure the development of new techniques and technologies for the 21st century, these disciplines therefore require an identity and research home at the NIH that is independent of the existing institute structure. So hard to imagine. I mean, think back into the mid-90s when this was actually written. We didn't quite have all of those tools and technologies that we currently appreciate and use widely today. But with that kind of foresight and a substantial resistance. So I'd like to point out that the NIH director at the time, Dr. Harold Burmis, was quite opposed to the formation of NIBIB. It was a very controversial topic. I've fortunately had many opportunities to interact with him personally since then, and I can say he has reversed his opinion. He is very much in favor of it and believes in the really outstanding work and high impact of our community. But it was controversial at the time, and I think that's an important point to bring out. It's a theme that will sort of be running throughout my talk. So in this language, there's the stipulation that this institute be independent and different from the existing institute structure. So what is that structure? Not everyone knows this. I've only been at NIH for 2 years, and I'm still trying to figure out the structure of the NIH. It's pretty complicated. There are 27 institutes and centers. It's roughly a $40 billion a year organization. I believe it's up to about $43 billion. We spend all across all these institutes a little over $1 billion on commercialization each year. So it's an amazing venture investment activity that is going on. And I want you to remember that number in the context of RADX, where that's about the amount that we have been spending in RADX in just 1 year in a single program. So where is NIBIB in this structure? It's way down in this lower right-hand box. And our vision is really to restructure the NIH, re-engineer, and have engineering at the center of the future of health. So that's really the vision of our community, and we're trying to communicate that through the NIBIB to our colleagues all across the NIH. By putting us in the center, we're able to take technologies and drive them into important problem areas all across the biomedical research domain. What's our size? Roughly about $400 million a year is our annual budget, and we support roughly about 1,000 grants. And this is relatively small. It's about 1% or a little less than the total activity of the NIH. So what is the content, and how do we define what those things are? How are we engineering the future of health? And I think all of you know this somehow intuitively, but I always like to put it in one place to help bring us all together. We're a community that's doing many, many different things, but in some ways, we are all organized by the way that we think. And at the center of the way that we as a bioengineering community think is the idea that modeling, computation, machine intelligence, the mathematical techniques that we use and drive forward are a central organizing feature. So we can use them to describe biological processes, describe complex emergent behaviors in biologic systems. We can use modeling computation to simulate how instrumentation works and create virtual machines or virtual instruments. We can make digital twins of humans. We can combine all those computational methods with our experiments, and these kind of move into 4 major domains. One is in engineered biology, and engineered biology is quite broad, and it spans from things like personalized organ simulators, which can be used for disease diagnosis, deeper understanding of how organ systems work, to synthetic biology, which involves looking at cells as integrated circuits, reprogramming those circuits, thinking of switches as transcription factors. So this is a rapidly moving area, quite broad and very exciting for our community. Another major component of our field are the development of sensors and point-of-care technologies. Those sensors span from wearable types of sensors to implantable sensors. In general, they involve a variety of different forms of energy transduction and then their transmission into digital health platforms. Point of care, I'll talk about a lot more as we try and take many of these advanced technologies and move them into rapid in vitro diagnostics for detection of COVID-19. In the lower left-hand corner, you can think of this as representing the big physics. You bring the human or the living system to the physics instrument. These are imaging technologies, and they span all the way from more personalized imaging devices such as ultrasound, and in this illustration, a head-only MRI, for example, that's being developed in Mike Garwood's lab at the University of Minnesota, all the way to the biggest of and most complex MRIs with the highest field strength and the highest possible resolution. And finally, therapeutic devices that involve a combination of energy delivery and energy and molecular activation. So these are really cutting-edge technologies that can be delivered to specific locations in the body, and all of the attendant computational approaches to optimize the selectivity and the impact of those therapies. So very broadly, these are the tools that our community has been developing and advancing in order to engineer the future of health. And where are they going? So here's an interesting statistic as we've analyzed the impact of NIBIB and the bioengineering community on biomedical research. So as I mentioned, NIBIB has about 1% of the total NIH budget, but over the last 10 years or so, there's been enormous growth in bioengineering all across the NIH. So you can see since 2008, there's been a nearly 80% increase in bioengineering across all NIH institutes. In 2019, it accounted for 13% of the total NIH budget. And we haven't done the calculations for 2020, but we know we've spent about another $1 billion in NIBIB just on the RADX initiative alone. So this is moving up into the 15% of the total NIH budget that is dedicated to bioengineering. And this is moving faster than the rate of increase of the NIH budget itself, which over that same period has only increased by about 26%. So it's easy to do the math and extrapolate. In 30 years, more than 90% of the NIH budget is going to be bioengineering. I'm confident of that. And, you know, you may smile, we may smile, but for those of you who've been around for 30 years or more and think back at what you did when you first started and the arc of the development of our technologies and their impact in human health, I think this is actually quite likely, it's not unrealistic, that much of what goes on is enabled by the technologies that all of you are developing. And as we as a community continue to grow and expand and move our impact into areas that have not traditionally been affected by technologies, this really will come to pass. So on that topic, our mission is expanding also directly into medicine, not just in terms of schools of engineering, where, of course, bioengineering has become a top priority, human health has become a top priority. We're seeing expansion into chemical engineering, mechanical engineering, EECS. We've seen enormous growth in the departments. So when NIBIB was first created, there were about 30 ABET BME departments in the country. There are over probably 120. Laura, you can probably tell me exactly how many there are, but it's got to be at least 120 now. There may be 130 or 140 departments in total in the country. So tremendous expansion and an embrace by schools of engineering of biomedical research, which was not the case before the year 2000 or 2002 when NIBIB really was stood up. So that's a tremendous impact. But it's going in the other direction as well. So medicine engineering partnerships are occurring in schools of medicine. Many of you are familiar with the University of Illinois Urbana-Champaign program, which has now pioneered engineering in medicine. The training is fundamentally embedded in engineering principles. And the second one is Texas A&M University, which is led by Rod Pettigrew, the founding NIBIB director. He's the executive dean of that program. And they characterize this training as physicianeers, the conjugation of physicians and engineers. And this is going very beautifully. So these types of programs will continue to expand as they develop standardized curricula. And as we as a society become more and more, I don't want to say dependent in a bad way, dependent in a very good way on advanced technologies that can improve access and outcomes for patients. So they really can drive human health, and there's enormous opportunity for economic growth and economic health. So part of what I've been able to do since I've come here is help build our National Advisory Council. And here's a picture of our academic members of our council. And they really reflect our community. And some of the principles, the founding principles of the council are attention to diversity. We know this is essential for the growth of our field. We're intellectually very diverse. We're curious and looking outward as a community. So having a council that reflects those principles and values is quite important. We embrace new ideas and approaches, and we are really fundamentally problem solvers in the best possible way. We blend technology with altruism, and I think that will be, again, a repeating theme as I continue with the talk and describe what's been going on with RADX. We also have the option and the capability within council to form a working group. We only have one working group, and that is one that I established in September of last year. It's on diversity, equity, and inclusion. This working group is co-chaired by Dr. Gilda Barabino and Dr. Rod Pettigrew. We also have Manu Plott, who's a professor of biomedical engineering at Georgia Tech, and Greg Washington is the president of George Mason University on that committee. So we look forward as an advisory council and working group to interacting with and engaging with all of you in the coming weeks, months, and years as we take on many of these challenges of diversity and training, expansion and inclusion and equity within our bioengineering community. And kind of on that topic, I wanted to draw your attention to this RFA, which some of you may have seen. This is led by Dr. Hannah Ballantyne and her office. She was the Chief Officer for Scientific and Workforce Diversity at the NIH, just left after a 5-year tenure, went back to Stanford to rejoin the academic ranks. But I had a chance to work really closely with her through the formation of this. And there's some really beautiful and interesting features to it. First of all, it's a common fund initiative with over $240 million dedicated to this. And one of the foundational features is the formation of a U54 network where institutions can essentially propose how they'll create a program where they will hire a diverse cohort, early stage faculty who would receive multi-level mentoring and professional development and substantial funds to launch their research programs and their research careers. But another really interesting feature to this is that the grants are designed to drive systemic and sustainable institutional culture change. So it's not just about funding those faculty, it's about funding that university to do better, to address bias and equity, provide mentoring, help people balance work-life issues. So this is a really, really interesting and novel type of mechanism that Hannah and her colleagues and many of us all across the NIH have contributed to the formation of over a few years. There's also the opportunity to apply for being a coordination and evaluation center that will work with the U54 centers to evaluate how efficacious this program is and get quantitative metrics for measurement. So in the lower left-hand corner, I want to draw your attention to this URL where you can look at a webcast. It is a 2-hour webcast, so it's a bit long, but you can fast forward through it at your pleasure. It's got lots of really useful information on it. And please don't hesitate to contact my colleague Zainab Aram, who is our training division director and our primary connection and lead for this particular program if you have questions. So the timing of my talk is good. The application due date is March 1st. Hopefully some of you have been working and thinking about this, and it would be just fantastic if we could get one of the first grants into the biomedical engineering, the bioengineering community. Another thing I'd like to brag about before I move into the RADX talk is our debut awards. And many of you, I think, are familiar with this. These are challenges to undergraduate teams, and we are now offering $115,000 in prizes. We've been able to recruit the National Cancer Institute for cancer-related awards, NIMHD, National Institute for Minority Health and Health Disparities, for new technologies. So these prizes go directly to the team. They're cash awards. Our ambition is ultimately to bring in all of the NIH institutes to be able to sponsor awards. We want to see this program grow, and we want to see more applications. It's been growing every year, and we're very, very proud of it. Very beautiful designs. Another thing to point out is that traditionally this has been about developing prototypes, working prototypes, but in this current climate where it's very difficult to get into laboratories, and that's not always easy to do, ideation projects can be competed for, and awards are given in those areas as well. So now I'd kind of like to move in with that little bit of a background about NIBIB, where we came from and where our ambitions are as a community. Let's talk about what our strategy has been to deal with the COVID crisis. It's been in three major areas of great strength, I think, in our community: imaging and artificial intelligence, digital health platforms, and diagnostic test technologies. And I don't really have time to go into the first two. Maybe you'll have me back at some point in the future and I can talk about some of those efforts, but I'm going to go into detail on the diagnostic test technology story. So this really came about as a result of an unexpected opportunity. Some of you may have followed that on April 24th, in the fourth congressional appropriation, $1.5 billion was appropriated to NIH for diagnostic test technologies. And this was a surprise to all of us. We thought there would be a significant appropriation, but nothing at that scale. And in fact, a $500 million line item was directed to NIBIB. And if you recall, I mentioned at the beginning, our annual budget is about $400 million. So there you go, in the stroke of a pen, we exceeded already that annual budget. And working closely with the Office of the Director, led by Francis Collins, we established RADX. We in fact had already kind of launched what we call RADX, Rapid Acceleration of Diagnostics Technologies, from a technology point of view. And when the Office of the Director had this substantial resources, we were able to create 4 different versions of RADX, one being the technology advancement, which is that $500 million NIBIB program. A second is scaling up technology platforms, which we called RADX ATP. A third is RADX RAD, which are very future or forward-looking technologies. And a fourth is RADX UP, a $500 million program that's designed to do testing and moving technologies into underserved and underrepresented populations. RADX UP is now launched in phase 1. I'll mention that briefly as we continue. It's about $300 million that's been allocated, and we're about to move into phase 2. So this is up and running. The most mature and longest ongoing programs are the ones that I lead with Jill Heemskirk, who's the Deputy Director of NIBIB. We immediately formed partnerships with BARDA, the FDA, the Department of Defense, CMS, CDC. So this became a trans-government effort. BARDA, in fact, added $300 million to our program, and Congress just recently appropriated another $100 million to the RADX program. We launched RADX 5 days after this initial appropriation, probably the fastest start ever from congressional appropriation to the launch of a federal program, I think foreshadowing the kind of accelerated pace that we would implement in order to take this project on. So at the outset, what we wanted to do, and this is the original goals of the RADX Tech and ATP program, were to expand testing technologies. It was clear if you go back into March and April, the country was only doing a few 100,000 tests per day. Those tests were coming primarily, in fact, almost all from laboratories on symptomatic individuals. If you fast forward and you start to look at the growth, and this figure is taken from the COVID tracking project, so it's fairly recent, we can see the continued growth of the number of tests that were being done per day, that are being done, to roughly 2 million tests per day. Now, what's important here is that this number reflects laboratory tests still, because of the way that tests are tracked all around the country as they are delivered to public health labs and to the CDC. What we've been able to do is expand that so there are now many, many options for point of care technologies, and tests are really optimized in terms of their operational and technologic performance to match community needs. So that's been really the original goal of the project. But what is both fascinating to see and also kind of scary is that there are probably at least 2 million, if not more, tests per day that are lateral flow assays, rapid antigen quick tests that are unreported. So it's hard for us to see their impact just in terms of monitoring for public health. But they are returning results to individuals who are hopefully taking those in and modifying their behaviors appropriately so that there is no further spread of the virus in the case of positive tests. So this story, this rapid expansion, where we're going from lab dominated to point of care dominated with many, many point of care tests, is kind of the story of the RADX effort. To make this happen, we leveraged an existing network that we had invested in for 13 years. This network was launched, again, by my predecessor, Rob Pettigrew. We expanded it with the RADX program. Some might say we hijacked it in order to be able to address the needs of COVID testing. There are over 1,000 experts and contributors all around the country that are making contributions to this network. At the core is CIMMIT, which is the Innovation Institute at Mass General Hospital. They're the coordinating center. Additional nodes are at Johns Hopkins, Georgia Tech Emory, Northwestern, and UMass. We added the nonprofits VentureWell and Biocom into this structure. And overall, the entire structure allows us to do some very unique operations very quickly. First of all, review and fund projects. Second, test and validate technologies. So Georgia Tech Emory, for example, has the validation core for the entire network, and every technology that comes through has independent validation of performance by our validation core. There's also clinical studies where there's standardized trial design in our clinical studies core, which is at UMass. And finally, there's a deployment core that's designed with optimizing the implementation, supply chain, and manufacturing. And I'll go into a little bit of detail on those cores. But the bottom line is, with the expansion of this network, we're able to do things very, very fast and very efficiently, including providing expert guidance on a continuous basis for everything from technology to regulatory, so that projects that make it through are going to have emergency use authorization and be approved by the FDA. This network is also connected, as I mentioned before, we have RADX UP, the Underrepresented Populations Program. So we are connected through coordinating centers so that all these testing technologies and the capabilities of the technology component are moved into underserved and underrepresented populations as well. So the main engine behind all of this is what we call an innovation funnel. And for those of you who are interested in innovation and entrepreneurship, you've seen this type of concept. What we've done here is reduce it to practice on a very, very large scale. At the outset, with rolling submission that began on April 29th, we really sent out a call to the innovation and entrepreneur community all around the country, which is largely enabled and facilitated by small companies and academic groups that are coming from bioengineering and similar types of efforts. So you can see the composition of the submission of applications. Approximately 3,000 applications were started, which was quite overwhelming. There ended up being over 700 complete applications. We have a series of stages in this funnel with reviews and milestones. Some of you may have heard of the Shark Tank process. So 137 of those applications made it into the Shark Tank. That's a 1-week-long intensive review where every project is matched with at least half a dozen experts so that the project is optimized, strengths, weaknesses, opportunities, and threats are identified, and budgets are articulated for the movement of that project all the way from concept stage into manufacturing and deployment. So that's one of the very unique features of this program. Generally, an NIH program is supporting early stage innovation, perhaps some prototyping, but to go as far as having the ambition to scale up and manufacture and deploy millions of testing technologies per week, and now even per day, is really quite unheard of. We managed to have an impact with that manufacturing and scale up because of the timing and the regular cadence of all of these events in as little as 5 months. So within a 5 to 6 month basis, what normally takes 5 to 10 years, we've been able to compress down. So there are currently 25 projects in phase 2, which is really the penultimate component of this funnel. Those are the manufacturing and scale-up projects, and they are roughly receiving $500 million. So here is a kind of a snapshot of those projects. On the right, you can see they're broken down in point of care and home platforms, laboratory platforms, and lab products. You may recognize some of these, and you may even have heard of some of the announcements. So for example, this company, Ellume, which is an Australian company, just recently received the first over-the-counter emergency use authorization. It's a quick antigen test in a lateral flow assay format. I actually have one right here. It's a small plastic cartridge with a lateral flow assay inside of it, and it utilizes really advanced components, quantum dots, integrated optoelectronics, a really beautiful readout system that instantly connects with your smartphone through Bluetooth. So there's some very nice technologies that are being advanced through this. Another one is this Luminostics platform, which is also a lateral flow assay, and it uses persistently luminescent nanoparticles. You can see in the upper left-hand corner, there are handheld RT-PCR devices from Mesa and Visby. So just as a way of seeing kind of a scale, this is a PCR instrument with sensitivity that's comparable to laboratory PCRs, but it has a cartridge that's removable. The cost of goods of the cartridge is around $25. This can be used in a variety of settings, the same for the Mesa. And you can see there are even support for mobile platforms. The first electronic reader-based lateral flow assay developed by Quidel. Some of the laboratory platforms are notable for their ridiculously high throughput. So for example, the Broad Institute is doing 100,000 tests per day. They just crossed the 10 million test mark. We just saw that today. You may be familiar with Helix, as well as Illumina, and some of these other large laboratories that have been supported for expansion. CRISPR technologies with Mammoth Biosciences, new ways to concentrate samples with nanospheres or nanoparticles, as well as swabs, which are providing very critical replacement for some of the supplies that many of the manufacturers are experiencing. So I described those 25 winners of large-scale manufacturing grants, but there are many, many projects that are very exciting that we're trying to support and keep alive that may not have made it through that manufacturing expansion stage, but are extremely important and could eventually, we think, make powerful contributions. So we've been able to redirect those into an existing NIH network, the SEED network, that's led by Matt McMahon at NIH, where we have another 50 early stage tech projects that are receiving some funding, continued industry coaching and mentoring, and additional training and resources. So what's the impact of all of this? If you look at the cumulative capacity of number of tests that we've produced, and we effectively, remember, we launched the funnel on April 29th. So going through the process of selection and analysis and funding and all of the things that have to happen before you get to manufacturing and scale up started to appear in September. So our total capacity in 2020 was supporting 94 million new tests. Roughly half of them were sold. So there's a little bit of a gap between tests produced and tests sold, and I'll get into that in a second. But by the end of the year, RADX supported activities were producing around 1 million tests per day. And if you go back and think about where we were at the time RADX was launched, the country as a whole was only doing about 250,000 tests per day. We've contributed substantially to that expansion, which was the goal at the outset. Many of these companies, through the process that we have baked into this, have received emergency use authorization, and that's through our constant interactions with the FDA. But in addition to that elite 4%, there are about 150 companies that have been supported overall and are still staying alive, and hopefully will be able to get private capital support and continue to advance their work. There are many investments that are kind of beneath the surface that you can't see. I haven't been able to disclose publicly yet. And based on those plus these 25, we're projecting that by the end of March, we will have more than 2.5 up to around 3 million tests per day that are produced both by these existing 25, as well as probably about 4 or 5 more that will be disclosed in the coming weeks. Now, as I mentioned, there is a bit of a gap between tests sold and capacity, and paying attention to that gap, I guess minding the gap, is part of one of the missions of our deployment core. This is led by Nancy Gagliano at CIMMIT, the Innovation Institute at MGH, and really the lead product of this implementation core is a website with a calculator called When to Test. So I encourage you all to check this out. It's whentotest.org, and it's a way to evaluate it for a given size of an organization and a variety of different interventions like mask wearing, whether or not you have contact tracing, whether there are unmasked group activities. What are the effects of all of those interventions and tests of given type and sensitivity on reducing the spread of the virus in your organization, in your structure? And you can scale it from, you can imagine if you're a family of 5 or a small community, a classroom, a business, so you can query using this calculator what you would need in terms of test performance and in terms of cost in order to break the chain of transmission. This is essentially the front end of a series of playbooks that are being created to advise K through 12, colleges and universities, businesses, organizations and structures that do not have a clinical expertise or infrastructure on how to stand up testing programs. And just overall, it's a mechanism which is a little different from what we do in the technology world. It's reaching out to try to disseminate technologies and connect people with solutions that will help solve problems in a more efficient and effective way. One of the cores is a validation core, and this is led by Wilbur Lamb and his colleagues at Emory Georgia Tech. And we're quite interested in this core in really quantifying performance of the different technologies. And it's really quite clear that there is a performance gap between the quick antigen tests, which have limits of detection on the order of about 10 to the 5th copies per mil and higher, and the performance of PCR tests, which may have sensitivities, limits of detection on the order of 1,000 or less, maybe 100 copies per mil. So that means they need to be deployed in different ways, those particular technologies, and we're also seeking approaches to bridge that gap. So in general, there are 2 major strategies. First, we're seeing many exciting new technologies. They're continuing to emerge from our funnel and having support that appear to have performance that reside right in between. CRISPR, we're seeing advances in microfluidics platforms, nanoparticles of all forms. Single molecule detection is also one of the components of our portfolio. And there are some really exciting waveguide-based technologies, both acoustic and optical waveguide technologies that will be emerging that are able to detect binding reactions that take place on the surface of waveguides and transduce that information with exquisite sensitivity. And that's a much different platform than doing it in a lateral flow assay format. But we're also looking at new protocols for some of these handheld and portable PCR technologies. Many of you think of pooling as something that might be going on in big laboratories. But imagine if you can pool a point of care technology like this, bring it into a classroom and test with a standard protocol an entire social pod or network, a whole class of 10 or 15 students, or a work crew or a team. Once you do that, you get an answer within 30 minutes if any one of them is positive, and then you can further break that down into smaller and smaller groups and get answers with a very high level of sensitivity that exceeds the sensitivity. It's better in performance than lateral flow assays. Now, they are more expensive intrinsically, but if you pool 10 or 15 people, then the cost per person becomes very much compatible and aligned with a lateral flow assay, an inexpensive assay, and can even move into the dollar or so per person category. So these are rapid. They report an entire social network, which if any one of those individuals would be positive anyway, public health recommendations are that they are all tested sequentially because they are contacting each other and be quarantined or isolated anyway. So it gives you that answer very, very quickly. The clinical studies core is taking these concepts and these technologies and moving them into larger clinical settings, not giant studies, but controlled settings where we can evaluate the performance of the technology. So this is led by Dave McManus and Laura Gibson at UMass. And I'd like to highlight a couple of these. One is a multi-site study that's going on at UMass, University of Illinois Urbana-Champaign, and Johns Hopkins University. We're expecting about 100 or so students to enroll in this. And this is evaluating the value of longitudinal sequential lateral flow assays. So as I mentioned, there's a performance gap between PCR and lateral flow, but many have argued that if you just do lateral flow 2 or 3 days in a row, if a person is infected, you'll catch the expansion of the virus on the time scale of that viral expansion. And if you do multiple lateral flow assays, you will capture the infectiousness of that person. So this study is really designed to evaluate that. How many lateral flow assays do you need to do, and what is the timing of their administration with respect to PCR? Every individual in this study will have RT-PCR from nasal swabs and saliva in addition to lateral flow assays every day for 2 weeks. Samples will also be saved and evaluated for infectiousness using an assay developed at Johns Hopkins. Another study, which is ongoing right now, is at UMass and Northwestern, and that's designed to look at self-sampling at home in conjunction with a digital health platform, an app that provides instructions for use and helps facilitate the interpretation. We think everyone will adopt apps, but we're technical people. We think it's quite normal. So this is really designed to evaluate the receptivity of the general public to use apps in conjunction with testing technologies in their homes. And the third major study that we're involved in, and this is a partnership, this is being led by Dr. Collins and working in partnership with the CDC, is really the big question. And we call it the big study. And we'll see if we can get this launched. If everyone in a community had home tests, would their deployment actually break the chain of transmission of the virus and reduce the prevalence in that community? This is kind of the ultimate ambitious study. Keep your eyes open for this. We hope to be able to launch it within the next few weeks. Just as a way of helping kind of see what this lateral flow assay challenge is, on this first study that I mentioned that's taking place at the University of Illinois, what you see are some first results. This is from one subject that show on the y-axis CT values. And just to help remind everyone, if the CT value goes down, there's more virus. There's a greater viral load. So what we see is a very nice increase peak of infectiousness here from a nasal CT, where there is the lowest CT count. This is a saliva sample, which has different kinetics, but still is dropping off over time. After you hit this peak, we see a drop. And every day for the first 5 days that this individual is tested, you see a positive lateral flow assay. And once you're past this peak, there are more RNA components per virion. Individuals are shedding the virus. And it's generally thought that lateral flow assays are better measures of infectiousness. So we will now have all of the data with infectiousness that correspond to the kinetics or the dynamics of all of these studies. But this is very encouraging and tends to suggest that lateral flow assays can indeed capture infectiousness over the range of CT values that are really quite important that reveal that. So really finally, as I mentioned, the big challenge is to pull all this together and get tests into people's hands and get them into people's homes. And we think the digital health platforms are going to provide an important component And this really illustrates where we are. And in fact, it illustrates a real technology that we've been supporting from a company called Care Evolution. They've made a platform called Safer COVID. So first of all, it provides detailed use on instruction with timers and animation. It facilitates symptom surveys, so you can track your symptoms every day. It also incorporates the ability to use out-of-the-box wearables and do that type of tracking. There is potentially the ability to integrate readers. So with lateral flow assays, which are simple dipstick types of approaches, it's important to be able to interpret the darkened lines, the blue lines, and using machine learning approaches or simple types of imaging approaches, one can capture a photograph of your test and have that interpreted and provide a record of it as well for public health. This facilitates then digital contact tracing. One can connect to electronic health records through HL7 or FHIR format, which preserves personal health information. And this is really advanced quite substantially as people are trying to develop these types of tools, and that's integrated into this app as well. And potentially, this can be integrated into some sort of a device, a way to securely provide proof of health status if that's needed. So let me try to summarize everything and try to put this in perspective. To get to this point, we've leveraged and expanded an existing NIBI network. And usually when in the government, we talk about expansion, we talk about increasing of bureaucracy and slowing things down. I think quite the opposite has happened here. We've used engineering principles with purpose-driven design to put in new processes to give us what I think is really unprecedented speed and impact. One of the things I think we've revealed is that off-the-shelf solutions, we kind of know that in our community, but the public health community, the policy community really hasn't understood that until this point. And I feel that this effort has helped people become much more aware of the power of the kinds of innovation and entrepreneurial activities that our community can lead, and that purpose-driven technology can overcome key limitations that we need in order to do better as a society. And kind of on that point, there's been an unexpected pairing, a connection, a collaboration going on. Many of my talks have been given to people from public health. And I've had to suppress the urge to say things like quantum dots and ASICs and nanoparticles and things like that in those communities. But they really are beginning to embrace these approaches. And I think this is a wonderful opportunity for our community to continue to expand that partnership, reach out to your colleagues in public health and policy. Technologies that are purpose-driven can be transformational and can change the course and the progression of these kinds of fast-moving diseases, as well as many other public health issues that we're contending with. So what are our ongoing challenges? As I mentioned, we've made now about $1 billion investment in diagnostic technologies, which is quite unprecedented. I am not aware of a similar investment that's been made in diagnostic technologies, just that particular area. I'm not familiar with that. This is pretty substantial. We need to leverage this for other diseases and for future pathogens. So many of the platforms that we're supporting are reconfigurable and can be adapted. And we're expecting not only emergency use authorization, we're putting pressure on the manufacturers to be able to get 510K and PMA so they become permanently embedded within our diagnostic structure. But another really interesting thing that we're running up against and learning is that our regulatory, healthcare, and our reimbursement systems are optimized for detecting disease in individuals. We all kind of knew that, but what we didn't fully appreciate is that they are absolutely not optimized at all for screening and surveillance, prevention of disease in populations. This is a big challenge going forward, and I think it's going to require voices from the bioengineering and technology community to help drive this problem forward and come to solutions. RADX itself, we believe, is a general platform for acceleration. We plan to embed this within NIBI Structure disseminate it to our colleagues across NIH and beyond. I think it's also a wonderful platform for academic groups and for universities to consider as well. Many of you have your own innovation programs with competitions that are going on internally, so it can be quite useful there. And kind of my final summary of all of this, the Super Bowl's coming up. This has been really like a Super Bowl for our field. We've dramatically expanded our budget. Again, a $400 million a year agency. We've doubled our budget over roughly a period of 2 years consecutively. We've been able to implement this vision, engineering the future of health, which is really happening tangibly right before our very eyes. And galvanizing a community, I think, is an important thing. Hopefully we all can take pride in this and imagine other types of challenges that we as a community can take on, and show that there really is an opportunity for broader societal and health impact through advanced technologies and innovation. So I'll stop there, and hopefully we have some time for questions.
Yes, Dr. Tromberg, thank you so much for a very inspirational talk. I think that it's really remarkable to see how this effort really advanced so many cutting edge technologies like CRISPR and nanoparticles, all integrated and in such a short period of time. Most of the questions, though, are not about the technology, they're about the process and how you did that. So I'll read out a few questions to you, because I think there's a lot of interest in how you pulled this off. So the first one is the development of COVID testing technologies and vaccines is a great example of technologies translating from bench to bedside and marketplace. It's amazing how quick this process can be. Does NIBI have plans or programs to facilitate and speed up other technology translation after COVID?
Yeah, that's a great question, and I'm hoping, so we are going to take steps within NIBIB to create a structure that will allow us to preserve the process. So we'll create a permanent RADX structure. RADX, we launched basically like it was a startup, and within 5 days, we had to have this program up and running, or we decided that we would get it up and running, and that involved bringing many people in from other institutes on detail, other government agencies, hiring new people within NIBIB. So if any of you have launched a startup with the hurry up, let's get it done, that's what we did. But now that we've gotten an operational base behind us, our ambition is to make this a permanent structure and then take on other challenges and programs in partnership with our community, our NIBIB community, as well as with other NIH institutes. So you can imagine every institute is doing bioengineering. They all could benefit in cardiovascular disease and diabetes, in metabolic disease, in a whole range of problems that would be potentially solvable with new technologies or addressable by moving through a process like this.
I could definitely see a lot of applications. We have, the next question is, are there any interesting lessons about how to make teams from different universities, and I guess also from different companies, successfully communicate and work together, especially during COVID?
So this has been one of the most gratifying and spectacular results, and everything has worked because of that. It's that altruistic intent and desire to work together. Many of the people within the network that we're supporting have competed against each other in business over the years. They've all come together to solve this national problem. And so we're seeing this contribution to the greater good. At the outset, that's how we framed it. We essentially sent a call out to our community saying, join us, we need your help. This is, I think, a really good example of what a community can do when it comes together. Whether or not we'll be able to maintain that spirit in future innovation funnels and activities, I don't know. But we've certainly seen this through the course of the pandemic. And it's not just in the United States. We have interacted extensively with groups all around the world and have advised and collaborated with foundations and activities throughout the world, because this is a global crisis. It's a global problem, and we're very interested in helping contribute to that.
Okay, now when the NIH supports the development of point-of-care tests that will be commercialized, does the government retain control of the IP or otherwise benefit from the resulting revenue in this case?
No, the standard IP rules for support do apply. And what we've learned is I think if you look statistically at the successes, they all have had foundational IP. And what we've done is really help iteratively optimize and move that forward, and then provide resources to get to manufacturing. And there are many, many different versions of that. But in general, groups that were so early on that they didn't have the foundational IP or the early prototypes, while the ideas were really perhaps quite exciting, they didn't have the capacity to get to the particular time pressure of thousands of tests per day or millions of tests per day. So it's too far to go if your IP is that immature. So in this particular effort, we were really supporting mostly small and mid-sized companies that already had a substantial amount of that worked out.
That's interesting. I don't think that would have been obvious to us. So that's great. Great to know about.
I'll show you a physical example. This from Illum, they were doing maybe 1,000 of these a day. By the end of March, they will be doing about 600,000 a day. But if they didn't have already the integrated optoelectronic design and the quantum dot reporting system worked out, they would never have been able to be in a position to make this work. So we didn't. Now, when they had components that they were having trouble with, we were able to provide guidance and support and advice to work through those problems, and we are committed to continuing that. But fundamentally, they had to have those things worked out.
All right, okay, so should the RADX program need to be used again in an emergency situation? Is there anything about the program, particularly early stage, that you would improve upon?
Of course, I'm very biased. I think the RADX program, similar to other programs that we've seen, so the Operation Warp Speed for the development of vaccines, and the ACTIVE program, which if you're not familiar with, I suggest that people take a look at that. That's been a program to develop therapeutics. Monoclonal antibodies, in particular, have been a very beautiful outcome of that. It's a public-private partnership consortium. That accelerated effort has changed our way of thinking about what we really can accomplish in a short period of time. I think we've iteratively optimized in RADX on this process. How we might change it would be dependent upon what the problem is and what the time pressures are. So I think that's the beauty of having an innovation funnel and the ability to design it with stages and gates and time pressures that are appropriate for the problem itself.
All right, we have time. We have 1 minute left. You want to take a racial injustice question? So giving a growing impatience for action from the government to take actions against racial inequities, is there something that could be done at the level of an individual institute? I think that's, it says individual to better support Black bioengineers in academy and in industry to achieve equity and federal support for funding.
Absolutely. I think that you'll hear kind of in the coming weeks about efforts that will be going on all across the NIH, as well as in individual institutes that will substantially address those, or at least begin to address those issues, and really try to create entirely new structures to address structural racism. So that's been percolating. There I think some of you may be familiar with an executive order that was recently rescinded that made it difficult for us to sort of go into details on that, but that's been rescinded, and that information will be coming out really soon, led by the NIH, but also, as I mentioned, we have created a working group within NIBI that will be our lead for communicating with you, our community, and we are going to have some very unique structures and solutions optimized for our particular community.
Perfect. Thanks for taking all of those questions and for your time spent with us. I know that now you're going to go off and spend some time with trainees, and we appreciate your time ever more, even for that. So we are giving you a virtual round of applause. Thank you so much for so much that we learned.
Thank you. Good to see all of you.
Good to see you.